What's poppin', dogs? Mr. Allen here with some simple and compound interest application. We got Snoop Dogg in the house. He is setting aside some money in an interest-bearing account. Now, one of these accounts earns 4.2% compound interest, compounded annually, and the other is 6% simple interest. Now, he plans to invest $3,000 in the account, but which one should he choose? We gotta help Snoop D-O-double-G out with this one. So, obviously, the amount of time that he leaves this money in there is going to play a role here, but let's just see if we can work with some numbers. Shall we? We shall. All right. So simple interest just means you get 6% on the initial deposit here. Let's figure out what that is. 3,000 times 0.06. That's 180 bucks. Okay. So the simple interest, we'll do compound, and then we got simple. So versus simple. All right. Nice little T-chart there. Okay. So for my simple interest, we're getting, we said 180? Yeah, $180 per year. All right. It's not bad. I mean, the 6%'s nice. The 6%'s better than the 4.2. Does that mean that it's better? I don't know. All right. Well, let's see if we can write up maybe a little equation that we could, work with, because we'd have $3,000. So $3,000 in there in the first year, plus 180 bucks would give me 3,180, plus another 180 in year two would give me 3,360. Let's maybe make a T-chart within our T-chart, shall we? I think so. All right, let me get another color here. So let's say T for time, and then our money. All right. So we got, initially it's 3,000. After 1 year, it was 3,180. After 2 years, 3,360. After 3 years, 3,540, so on and so forth. Okay, that's enough for that one right there. What about our compound interest one? Well, it's 4.2% initially, right? So 3,000 times 0.042, that's less money. But then when you do if you add 3,000 to that, so add 3,000, then I'm going to multiply that by 0.042. And my interest is higher the following year. But then I'd have to add this seems like a lot of work. I'd have to add the 3,126, and then I got to multiply it again by 0.042. And then I got to add the previous one that's up here. It's getting messy, dude. This seems like a lot of work, right? A lot of work here. I don't know. Maybe there's a better way. There is. Okay. So let's jot down first off that it's 4.2% interest. Okay. So 4.2% compound interest. We can write a function for this thing here. We can write a function, A of t equals my initial $3,000 deposit. We're going up by 4.2%. So if I did 1 plus 0.042, raise that to the t, now I have a working function that can calculate the amount of money I have in this account year after year. That's dope. All right. Now I can write one for this one over here as well. So let's do that, right? Let's make a function for this guy. We'll say A of t for this one is going to be still 3,000, right? But then I'm just adding 180 bucks. So 180 t. You could also have it 180T plus the 3,000, but I'm adding $180 every year, okay? But here, we're tacking on 4.2% onto the new amount. That money is making money, and the money that made money is making money off that money, and the money that made up money off that money that made money off the other money you made is making money off that money, and it just keeps on happening, right? The money making money. So let's do this. What if I plug this all in, and let's see what we have like after 10 years, okay? So let's do that. 10 years. So 10 years in. 10 years in. What are we going to have? Well, this one's pretty easy to figure out. 3,000 plus 180 times 10. 4,800. But this one here, if I did A of 10, it's 3,000. 1 plus 0.042 times 10. Or sorry, raised to the 10th. 3,000, parentheses, 1.042, close them, raised to the 10th power. We're catching up, right? It's still not better, but we're catching up. What if we did 20 years? Okay, first off, I'll write down the 10. 4,526.874, so 87. Still the better account. But how about like I said, in 20 years? Let's go 20. Maybe Snoop's in for the long haul, right? Maybe he's like saving money for something. I don't know, like something, whatever. All right, so after 20 years, it's $6,830.86. And then the other one, 3,000 plus 180 times 20. What do we got now? Ooh, this one's the winner, right? It's got 6,830 versus 6,600. So somewhere right around that, maybe probably 18 and 19 year mark. We can even just test it here real quick. Let's do like 18. And then if I test this one, change this to an 18, what do I got? Okay, so about year 18 it looks like, because then I bet at 17, this one's not as good. So let's see here, 17, hit enter, this guy, year 17. Okay, so between year 17 and 18 is where this one takes the lead. So if he's holding on to this thing beyond 18 years, right, maybe he's putting money away for one of his kids or something like that, so when they turn 18, they get a lump of sum money. I think he's got more money than this anyways. But after 18 years, this is the better one. For the first 18 years, this one right here is the better one. Okay, so depending on how long a person's holding onto this account would dictate which one is the better option, right? So there we go. A lot of information there, guys. You can even plug these things into your graph them solve, but we're not really quite there yet. We're kind of just playing around with some numbers, trying to write these different equations. They're going to ask you to write an equation like this, one like this, and ask which one's better after 10 years, which one's better after 20 years, and you should be able to make that decision based on those numbers and the equations that you've created. All right, anyways, hope that helps. Hope you guys enjoyed this wonderful real-life application of simple and compound interest, because I felt that it was simply interesting. See you later.